All right, you're doing section 3.2, which is Rolle's theorem and the mean value theorem. We're going to start with Rolle's theorem, which states that if we have a continuous function on a closed interval from a to b, and you can take the derivative of it anywhere on the open interval from a to b, if f of a is equal to f of b, then there has to be at least one place in between f of a and b such that f prime is equal to 0. So it's saying there's a horizontal tangent somewhere. So not having this example down below, but here's a, here b, just to illustrate this property. F of a has to be equal to f of b, so they're equal. Doesn't matter what they do in the middle here. There has to be at least one point C where there's a horizontal tangent, and we do have a couple of those in this little scribble. But let's do our first example, illustrating Rolle's theorem. Find two x-intercepts of f of x and show that f prime is equal to 0 somewhere between these two x-intercepts. So if there's two x-intercepts, then f of a has to be equal to f of b at those 2 points. So we have to find them, set it equal to 0. You can factor it. And x equals 1 and 2 are zeros of our function. So they're saying that there has to be somewhere in between there that has a horizontal tangent. So we're going to take the derivative of it. F prime is 2x minus 3. And a horizontal tangent means that our derivative will be equal to 0. So we have to solve for that x value. And that happens where x equals 3/2. So Rolle's theorem says there must be at least one point. Where f prime of x equals 0, which there is. We just showed that it was 3/2, which is in fact in between 1 and 2. That's kind of neat. Another example, let f of x equal x to the 4th minus 2x squared. Find all values in c in the interval from -2 to 2 such that f prime is equal to 0. So we need to show that before we can use Rolle's theorem, so the last one was just kind of saying show that it does, we have to have all the conditions of Rolle's theorem met. So we have to know that our function is continuous and differentiable on the open interval. So this is a polynomial, so it is continuous on the closed interval. And because it's a polynomial, we know it can take the derivative of it anywhere. On the closed open interval, I mean. So it has to, the function value at each endpoint has to be equal to each other. So we need to show that f of -2 is -2 to the 4th minus 2 times -2 squared, which is 8. F of 2 is 2 to the 4th minus 2 times 2 squared, which is also 8. So those two are equal to each other. So we know there is at least one c value such that f prime of c is equal to 0 in our interval from -2 to 2. Okay, so now we need to find it. Take the derivative. 4x to the 3rd minus 4x. Take out a 4x. Squared minus 1. And our derivative is equal to 0 at x equals 0, -1, and 1. We have those all 3 points are in between -2 and 2. So all 3 of these are zeros or horizontal tangents in our interval from -2 to 2. Okay, the next theorem, the next section, part of the section is the mean value theorem. So we have a continuous function on a closed interval and differentiable on the open, so that's the exact same thing so far. There has to be a number c in our interval such that the derivative is equal to the slope of the secant line. That's FB minus FA over B minus A. That's what the slope of the secant line is. Which we explained, it guarantees the existence of a tangent line that is parallel to the slope of the secant line through our points A, F of A, and B, F of B. So an illustration of this, we have A and B. Let's say our function goes something like that. There's our secant line. This is A, F of A, and B, F of B. And there has to be some point in the middle, let's say at this point C, such that the slope of the tangent line is parallel, which I made it look like it is. Okay, so let's do an example. Given that our function is 5 minus 4 over x, find all values of c in the open interval from 1 to 4, such that the slope at c is equal to the slope of the secant line. So first we need to find what the slope is. So we need to plug those in. F of 4 is 4. F of 1 is 1 over 4 minus 1. That's 3 over 3, which is 1. So there's at least 1c in our interval from 1 to 4, such that f prime of c is also equal to 1. So we need to find it. The derivative is positive 4 over x squared. We want to know when that's equal to 1. Multiply it across. 4 equals x squared. X is plus or minus 2. So the only one that's in the interval is x equals 2. That's our value. Okay, this is kind of a classic calculus problem. This is kind of a cool problem. There's 2 stationary patrol cars that are equipped with radar and are 5 miles apart on the highway. As a truck passes the first patrol car, its speed is 55 miles per hour. Then in 4 minutes, it passes the second patrol car when the speed is clocked at 50 miles per hour. We have to prove that the truck must have exceeded the speed limit at some time during those 5 minutes. So we're going to start by saying that t equals 0 is when the truck passes the first car. And the second car, since we're dealing at miles per hour, it's going to be easier. Instead of using 4 minutes, we need to change that into an hour. 4 minutes, 4 over 60 is 1/15 of an hour. And we're going to use s of t as our distance. That's always our position or distance formula. When we are at time 0, our position is 0, and at 1/15 of an hour, so when it crosses the second patrol car, we have gone 5 miles. So what is our average velocity? That's the slope of the secant line. S of 1/15 minus S of 0 over 1/15 minus 0. So 5 over 1/15, which is 75 miles per hour. So we're kind of using that mean value theorem. Mean value theorem to say the truck must have traveled at 75 miles per hour sometime in those 4 minutes, which is definitely exceeding the speed limit. Okay, and that was section 2 on the Rolle's theorem and the mean value theorem.